All right, class. I had some technical difficulties, and I think that part of the lesson. Oh my goodness, bug! I think that part of the lesson got, um, wasn't streaming. So I'm going to. Um, so I. This is a little bit further than I was when the video cut out. So I'm going to explain this part. Okay. So when the video cut out, I had said that we have this free body diagram right here. Okay. So the fact that the mass is moving in a horizontal circle means that the net force in the y direction has to be 0. Why is that? Well, because if the net force in the y direction was not equal to 0, the mass would be moving up and down, in which case it wouldn't be a horizontal circle, would it? Okay? So that means that this upward force has to cancel this downward force. So they are equal in size. So F cosine of theta equals mg. Divide both sides by cosine theta, and we get that the tension in this rope is mg over cosine of theta. Okay? In the horizontal direction, though, because it's moving in a horizontal circle, there is a force, a net force, in the horizontal direction. And since these two canceled out, since this canceled out with that, the horizontal force is F sub t sine of theta. So what I've done over here is I've set up Newton's second law in the x direction, and it's equal to m times the acceleration in the x direction, and I've plugged in F sub t sine of theta. And then that equals m times the acceleration. It's moving in a horizontal circle, so that horizontal acceleration is the centripetal acceleration. So that's why I plugged in 4 pi squared r over period squared for the acceleration. Okay, so then what I did is I took this equation for tension and plugged it in right there for tension. All right, and that gave me, so you have mg over cosine of theta, so mg sine theta over cosine theta. And then I used the fact that the radius of the circle is not the same thing as the length of the string. So I took this and went right there, okay, and plugged that in. So see how in the next line we have L sine of theta. And then I did some algebra, and we get that the period of the conical pendulum is 2 pi square root of its length divided by gravity times square root of cosine theta. Okay, so that's so the period of the conical pendulum basically depends on the angle that it's making with the vertical. Okay, and you can imagine if you had a conical pendulum and you spun it around really fast, the faster it goes, sort of the more the string is going horizontal. So if you had a really, really fast swing on your conical pendulum, it's going to be like this, right? And even faster, it's going to be like this. All right? By the way, the reason it's called a conical pendulum is because the string is sweeping out a cone, if you think about it, if you visualize that. So what if we took some data? All right? So we have this equation, period is 2 pi square root of L over G times square root of cosine of theta. Okay? And what if we took some data? We would probably take some data of period versus the angle of the string. That's kind of the most natural experiment to do. So we basically would take the conical pendulum and give it a kick with several different speeds, and so it would start going around, and we would see the angle that it's going around with, okay, and we would record its period. All right, but we can see that period is not related to theta, it's related to square root of cosine of theta. So that means we need to transform our data table to not period versus angle, but period versus square root of cosine of angle. Like that. Okay? And so our graph that we make if we did an experiment would be period versus square root of the cosine of the angle. All right? And so if we made that graph, we can see that period is kind of like y, and square root of cosine theta is like x, and the thing multiplying x is 2 pi square root of L over G. So this graph should look like a straight line, and the slope of that line is 2 pi square root of L over G. Okay? Boom. So now I'm going to get to the gravitation part. Okay. So what we talked about is there's this thing called the gravitational field. All right. And the gravitational field is denoted by little g. And basically what it is it's the acceleration due to gravity. The units of gravitational field are newtons per kilogram. So obviously, or you could use meters per second squared because it's an acceleration. Obviously, the gravitational field near the surface of the Earth is 9.8 newtons per kilogram. So massive bodies create gravitational fields. So the gravitational field is G, big G, times big M divided by R squared, where M, big M, is the mass of the thing creating the field, okay, and R is the distance from the thing. All right. So as you get further away from an object, the weaker the gravitational field becomes. Big G is a constant of nature, and its value is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay, so this is the main equation for gravity. And then the gravitational force is mg, just like the equation for the weight force, where g is the gravitational field experienced by the thing, and m is the mass of the thing not creating the field, but in the field, experiencing the field. All right? So that's an important equation. So what we can do is we can imagine that there is a central body, big M. And then that central body has a satellite. That satellite is little m. So the satellite is the thing experiencing the gravitational field from the star, or experiencing the gravitational field from the planet, something like that. We are going to assume that little m is much less than big M. Okay? And what that means is that the central mass is going to just be perfectly still. Okay? Like the Earth orbiting the sun doesn't really move the sun around very much. But if you had two objects that have similar masses, then it's not like one is in the middle and the other one orbits around it. They orbit around each other, like this. Okay? So this is going to be fixed, and we'll say that the satellite is going in a circle of radius big R. All right. So then we combine circular motion with gravitational, with the idea of gravitational fields, and we write Newton's second law for the satellite. All right, so we have force equals ma. The force that's making it move in a circle is the gravitational force, little m times g, and it's moving in a circle. So it's moving in a circle. So we're going to use the centripetal acceleration, 4 pi squared r over period squared. And what you can see is that the mass of the satellite cancels out. Okay, it's on both sides of the equation. And then I'm going to plug in the equation for gravitational field, which is big G, big M over r squared equals 4 pi squared r over period squared. Now, if I cross multiply, I get what's called Kepler's law. G m t squared equals 4 pi squared r cubed. So this is Kepler's law. All right. We can take this and we can solve for the period. Okay. We can solve that equation for the period, and then we can plug that in to speed equals 2 pi r over the period, and we can get the speed of a circular orbit. The speed of a circular orbit is square root of g big M over r. So that's another useful equation. Okay. So these are some of the fundamental equations in gravitational physics. So one thing we could do is we could observe a bunch of satellites. Like take Jupiter, for example. Jupiter has tons and tons of satellites. Okay? So Jupiter, we could look at the radius of the satellite's orbit, and then we could look at the time it takes to complete that orbit. And we could make a data table for all the different satellites. Jupiter has many satellites. There's, going to be 10 plus data points. Okay? These are related according to Kepler's law. But notice how Kepler's law is period squared and r cubed. So we transform our data table. Okay? So we have period squared versus r cubed. So we cube the r's and we square the periods. Okay? And so Kepler's law says that r cubed equals g m over 4 pi squared times period squared, like that. Okay? So we wouldn't want to graph r versus period. We want to graph r cubed versus period squared. And then we can see that r cubed is like y, period squared is like x, and gm over 4 pi squared is like the slope. So this graph will look like a straight line, and the slope is gm over 4 pi squared. Okay? And we could use that slope to calculate the mass of the central body. And that's actually how we know what the mass of Jupiter is, because we can't take Jupiter and set it on a scale. It's too big for that. All right, so that's my lesson. It's going to be in 2 parts because I had a technical difficulty in the middle. But yeah, I will